You know how you normally give directions, go a few blocks over, a few blocks up, but what if there was a better way? What if you could just point and say how far to go? Well, today, we're diving into a system that does exactly that, the super elegant and intuitive world of polar coordinates.
So let's start with a really basic question. How do we describe a location? Seriously, if you wanted to tell someone exactly where a point is on a flat surface, how would you do it? Your first thought is probably the system we all learned in school.
And yeah, that system is called the Cartesian system. It's like a city grid, right? Go 5 blocks east, then 3 blocks north. It totally works, but it's not always the most direct path. Polar coordinates are more like how we actually think. It's like saying, see that tower? Face it and just walk straight for 100 feet. It's all about two simple things, direction and distance.
Okay, so how do we take this cool, intuitive idea of direction and distance and turn it into a proper mathematical system? Let's break down the actual building blocks.
Here it is, the heart of the whole system. Forget about x and y axes for a minute. We start with a single central point called the pole. You can just think of it as the origin. From that pole, we have an initial line that stretches out to the right. That's our baseline. And with just those two things, we can describe any point with two values. R, which is the direct, straight line distance from the pole, and theta, which is the angle you turn from that initial line to point right at it.
So the most important thing to remember is that we always write these as r, theta, distance first, then angle. And that angle, theta, is always measured anti-clockwise. And here's a big one. Theta is always measured in radians. So, a little pro tip, make sure your calculator is in the right mode before you start. So we have these two completely different systems, but they're not separate universes. They're more like two different languages describing the exact same space. And being able to translate between them is absolutely key. Let's see how it's done.
Going from polar to Cartesian is surprisingly simple. It all just comes down to some basic trigonometry. If you just imagine a right-angled triangle, where the distance r is the hypotenuse, then the x-coordinate is just the adjacent side, r times the cosine of theta. And the y-coordinate is the opposite side, r times the sine of theta. It really is that straightforward.
Let's see it in action. Let's take the polar point 3 pi over 4. So our distance r is 3, and our angle theta is pi over 4. We just plug those values right into the formulas we just learned. The x-coordinate is 3 times cosine of pi over 4, and y is 3 times sine of pi over 4. And boom, you've got your Cartesian coordinates.
Now going the other way is also pretty direct, but there is one little trap you've got to look out for. To find r, that's easy, we just use Pythagoras' theorem. To find theta, we use the inverse tangent of y over x. But, and this is so important, your calculator might give you the wrong angle. That's why step 3 is your absolute best friend. Always draw a quick sketch to make sure your angle is actually pointing to the right spot.
Okay, let's try converting the point 5, -12. Finding r is a piece of cake. With Pythagoras, it's just 13. Now for the angle. When we calculate the inverse tangent of -12 over 5, the calculator gives us back a negative angle. This is where the sketch is crucial. We can see that the point 5, -12 is down in the fourth quadrant. A negative angle just means we rotate clockwise from the initial line, which lands us right in the fourth quadrant. So the sketch confirms that this time, the calculator's answer was the one we needed. All right, so we can define points and convert between systems. That's great. But why? Why bother with a whole new system? Well, this is where it gets really powerful. The true magic of polar coordinates shines when we bring calculus into the mix. Just like it says here, anything that has a natural circular or spiral shape becomes so much easier to describe with polar equations. I mean, trying to define a spiral with x and y would be an absolute nightmare of an equation, but in polar coordinates, it can be something as clean and simple as r equals theta. And think about this. With Cartesian coordinates, we find the area under a curve by integrating along the x-axis. But how in the world would you do that for these beautiful, complex polar shapes like a cardioid or a rose curve? It would be ridiculously difficult.
Luckily, polar coordinates give us this incredibly elegant formula. Instead of adding up tiny little rectangles, we're adding up the areas of tiny little pizza slices, or sectors. The area is simply the integral of 1/2 r squared with respect to theta, as you sweep from your starting angle to your ending angle. It's a beautiful tool for a complex problem.
So let's put this powerful formula to the test. We're going to tackle an area problem that, trust me, would be a real headache with our old Cartesian coordinates.
So here's our challenge. We need to find the area of the region that's outside the simple circle r equals 3, but still inside the heart-shaped cardioid defined by r equals 3 plus 3 cosine of theta. We're looking for that area that's trapped right between them.
We're going to follow a clear three-step process. First, we've got to find out where these two curves actually cross each other. That will give us the limits for our integral. Then we'll set up the integral itself. And finally, we'll crunch the numbers and find the area.
Okay, step 1, find the bounds. To find where they intersect, we just set the two equations equal to each other. So 3 equals 3 plus 3 cos theta. That simplifies down really nicely to cos theta equals 0. And on the unit circle, that happens at negative pi over 2 and pi over 2. Those are our bounds. That's the angular region we need to sweep through.
Now for step 2, setting up the integral. We're using our area formula. But since we want the area between two curves, we're really just finding the area of the big outer shape and subtracting the area of the small inner shape. So it's the integral of 1/2 times the outer radius squared minus the inner radius squared. The outer curve is the cardioid, and the inner curve is the circle.
And finally, we evaluate. Now, this part involves a bit of algebra and calculus, expanding the terms, using a trig identity, integrating piece by piece. It's some work, but it's totally straightforward. And when all the dust settles, we get our final exact area, 18 plus 9 pi over 4. It's a perfect example of how picking the right coordinate system can make a super complex problem totally manageable.
So, what's the big takeaway here? Polar coordinates are not just some weird mathematical curiosity. They're an essential tool. Anytime you're dealing with something that rotates, or spins, or curves around a central point, this system can turn a ridiculously hard problem into an elegant and even simple one.
We've spent all this time talking about flat, 2D space, but that leaves us with one last really fascinating question. What if we needed to go 3D? How would you describe the precise location of a planet orbiting the Sun, or a satellite in space? Could a system of angles and distances work in 3 dimensions too? Something to think about. Thanks for joining me.